Okay, kids, you saw me do some of this stuff in class, a little bit of an intro to logarithms. I need to finish that lesson for you now. It's pretty short. It really is just an intro to logs. We'll do more extended, advanced stuff when we are together, but this is just to get you used to what this new notation means and what it stands for, kind of. Okay, so we did this in class, and where they're talking about this what power business, and what does that mean? Well, they did it in this way because it kind of looks like the actual log notation. What power do we put on 10 to equal 10? That's what this is about. 10 to the what power equals 10, and the answer there, of course, is 1. And we did all those in class. These we also did, but this is a little more interesting. So when they're asking this question, basically, what power do I stick on 2 to make it 2? Well, that would have to be 1. What power basically goes right there. 3 to the what power equals 27. That would be 3. 5 squared is 25. 4 to the negative 2 is 16, and 2 to the negative 3 is 1/8. So again, we did those in class. Have a look at those if you need to. All right. So logs in general, this is how the actual notation looks. And if you remember from the video I showed in class, log base 2 of 8 is 3. That's how you read that. That's describing the same relationship among those numbers as that sentence and really as this sentence. Those all kind of mean the same relationship is going on. And it is kind of a bummer that we use 3 totally separate notations for those, and the notation kind of gets in the way. But again, the how to read this is, like, what exponent do we put on 2, kind of right in there, that makes 2 to that power equal 8? And the answer to that is 3. Okay, so let's just do some. There's a link to that video if you want to, I don't know, type that in, or maybe you can click on that if you download this the notes packet. Also, I usually at this point in the year I play this song off of YouTube, and it's a hilarious commercial from my childhood. It's a spoof commercial about a fake toy called Log. I might start singing that in class, so at least you know where that comes from. Okay, so here's a bunch more ways to practice. What exponent do I put on 2 to make 32? 2 to the 5th is 32, so that's just stuff you should do in your head. 7 to the 0th is 1, so that's 0. 8 to the 1st is 8, so that's 1. 2 to the, I gotta think about this. 2 to the negative 4, I believe, is 1/16. So this is negative 4. I guess I could leave those up and still have room here. 3 to the what is 81. That's 4. 3 to the, okay, now they're getting more interesting. 3 to the what is 1/27. Well, 3 cubed is 27, so this should be negative 3. 4 squared is 16. 10 to the negative 3 is that. And 5 cubed. You should get pretty familiar with a lot of these power numbers by now. And if not, you will, because you're gonna have lots of time to practice those through homework and things with your calculator around before you have to do them without a calculator. Okay, fractional exponents we never talked about before, or we haven't talked about them this year anyway. 4 to the half power equals 4, and why is that? Well, if you didn't know what 4 to the half was, you could think about doing this. That should equal 4 to the half plus half power, if you do that, and that should equal, well, 4. So yeah, that means we've got a number here times itself that has equaled 4. So yeah, that's what that means. It means if I had 2 of those, multiplied them together, I would get this thing here, so that means it is the square root of 4. Likewise, if I put 4 with a 1/3 as the power, that means I need 3 of those multiplied together to get 4, etc. One thing they don't describe here, which I kind of wish they would have, is something like this. You could think of that as either 4 to the 1/3 squared or 4 squared to the 1/3. Either way, that looks something like this. You can think of it either way like this too. It's like taking a cube root and squaring it, or squaring and then take the cube root. Those are all equal. So the numerator of one of those fractional powers kind of does what you would expect it to do. All right, and then if it's negative, it's downstairs. That's really all that means. That's what we've been used to seeing. So have a look at those if you need to. All right, so this leads to these kind of possibilities. If this could end up as a fraction, if 25, basically this is saying 25 to the what power equals 5. You might want to think about that this way first. 25 is 5 squared. To kind of solve that on both sides for really 5 being by itself, I kind of want to take the square root of both sides, or take both sides to the half power. That will make that 5 just kind of by itself. Because this is what I'm looking for. What exponent goes here on 25 to make 5? So this is actually half. Likewise, since 2 to the 4th is 16, I know that 16 to the 1/4 is 2, and that's what I'm, sorry, did I say negative? didn't mean negative, to the 1/4 is 2, so this is just 1/4. Okay, same thing with this one. Log base 8 of 2 is going to be 1/3 because it's the cube root of 8 that's 2. This one is, maybe I should say that here, 8 to the 1/3 equals 2. This one's a little crazier. 27 to the what power is 1/3. Well, this side is 3 to the -1. This side is 3 cubed to something. And I need the 3 times that box to be -1. So what has to go in this box is -1/3. So that's probably the trickiest one we have. Pause that and go back if you need to. Okay. If you remember just how logs are written in the first place, that these two things kind of mean the same thing in this statement, sometimes it's helpful if you're trying to solve something or figure something out to just reorder the statement if you're given one of these to convert to the other one. So here's a bunch of back and forth we have to do. If log base 6 of 36 is x, then that's the same thing as saying, if you look at that carefully, 6 to the x power is 36. Yeah. And yeah, you may have heard me say this before, like when I learned this the first time, the log is the exponent, so that thing's going to be the exponent, notice. And also the base is the base. That's kind of nicely written there. And then the other stuff just has to fall in place. So the exponent here is the thing that's by itself. The log is the exponent. The base here is 2, and the other thing goes right here. The base is 3, the exponent is 4, and the rest goes over there. The base is 5, the exponent is x, and the rest of the stuff goes in the middle. The base is x, the exponent is -2, and the answer is 1/16. The base is 64, the exponent is half, and the rest of the stuff goes like this. Be careful of parentheses on that one. All right, here's some interesting questions about how log works as a function. What power do I put on 2 to get -8? Well, that's never going to happen, right? There's no power of 2 that's ever going to equal -8. Likewise, there's no power on 3 that's ever going to equal 0. So you think about the domain of this, no matter what the base is, and I guess usually you probably say b, log base b in general of x, what possible numbers can go in there? Well, x has to be positive. We always talk about how b is always going to be, and this is the same kind of b as the b defined in our exponential terms, or exponential functions in the first place. B is never going to be negative, b is never going to be 1, really, because it's not very interesting. And if all that's true, if I'm talking about exponents that could go on those types of b's to produce something, the something is never going to be negative. I guess it could be 1, because I could have the answer be 0, and that's okay. So I could put it, and we did that before, right? Like b to something could turn out to be 1, that's okay. But the something is never going to be negative, and it's never going to be 0. So the domain of log as a function is only positive values of x. Okay, here's a weird thing in notation. You know how when you see an x and there's nothing in front of it being multiplied, you know that's actually really the same as 1 plus x? Or if you had a square root of something, and there's no number up here, you know you can kind of assume that there's actually a 2 there. That's the same thing as like 2 root y like that, like the second root of y. And here's a weird one. If there's nothing right here, you can assume that they mean that there should be a 10 there. It's the same as there being a 10. 10 is like the default. If you look on the calculator, it says 10, or it's pre-filled to 10, or if you don't put anything there, it'll be presumed to be 10. That seems like a strange assumption, and it actually does. They do call it the common log. Why did they do that? Well, here's a couple examples. The log of 100 is 2, because if you square 10, you get 100. Log 10 is -1, because if you put a -1 there, you get that. And you know, log, if I put 5 zeros there, the answer is going to be 5, right? So they use 10 as the common kind of default base because we live in a base 10 world, and if we're talking about taking anything to powers and counting up the powers quickly, 10 is a really easy one to work with. It's just the number of zeros that follow a 1. And yeah, it actually comes up more often than you might think. And it's kind of convenient, actually, that 10 is the assumed base. All right, we just have these last 6 problems to go, and that's going to be it. Shortest video ever. All right, so this is just about reordering things like this, but now to do that in order to solve for x in an equation. I guess we could have solved some of these. Some of these are actually kind of easy. But this is one of those things where, okay, so we're going to do these 6 right now. Once we get farther into this unit, we're going to have some equations that have some more complicated log rules. And when people start to get into those more complicated log rules, they forget about this one. This one's actually really easy. This is just apply the definition of log and rewrite things like in the other arrangement. And, you know, that's really actually pretty easy to solve, but it might not seem so, like at the beginning of this when you look at it. M to the fourth power is 81. Well, I can actually solve that because I know that 3 to the fourth power is 81. I should be careful, though, if it's an even exponent that I might be thinking about a negative that could also work for that. But anyway, that's not so bad. This is 2 to the fifth, and I know what that is, so this isn't bad. X to the third, well, again, you should probably know that one. 4 to the x equals 1. You got to think about that a little bit harder. That makes 0. And 64 to the 1/3. The cube root of 64 is 4. So we're talking about 2. Okay, we'll see if this recording works. See you in class.